Hello, everyone. So today I'm going to introduce our paper, Automatic Short Math Answer Grading via In-Context Meta-Learning. About the authors, so I'm a PhD student at UMass Amherst, and Sami is a PhD student from WPI, and Professor Houghton is also from WPI, and Assistant Professor Len is from UMass Amherst. So first, let's introduce what is the automatic scoring. So automated scoring is an NLP application usually deployed in the educational domain. It involves automatically analyzing a student's response to question and generating either a score in order to assess the student's knowledge or his skills. There are various types of the student responses. For this work, we mainly focus on the short answer grading, especially in math domain. Automated scoring approaches can potentially scale up human grading effort by training on a small number of example scores provided by human experts. They can automatically score a large number of responses. So that looks like these two questions. For part A, is asked for the measure of the HDCF. And that's a close-ended question because there's only one single correct answer. But for part B, it's asking for explain your reasoning. I'm pretty sure that all of you have different answer in your head, which may be correct in some way or other. So part B here is an open-ended question, and that is the thing that we are mostly focused on. So here is some examples show how what is the data set looks like for this paper. In this study, we use data collected from an online learning platform that contains student open-ended responses paired with score provided by human graders. So the scale is from 0 to 4. 0 is very poor, and 1 is poor. 2 is fair, 3 is good, and 4 is excellent. And for each student responses, it's paired with the corresponding question test and the question unit ID. Now we introduce the existing BERT-based methods. So first, what is the BERT and sentence BERT? And BERT and sentence BERT are both can use for sentence embedding. It encodes a sentence into a vector, and we can use this vector to do something. So similar sentence should have similar representations. So current state-of-the-art method is called the SPERT-Cabra. This method is based on the semantic textual similarity, where it first finds historical answer closest to the new student answer and assign the same grade for the most similar answer to the target answer. Also, there's some other method directly pass the response embedding to a classification layer to predict the teacher's grade. But the existing BERT-based method have some drawbacks. So the first drawback is that BERT and sentence BERT is not especially designed for mathematical language. So with this drawback, the solution is use the MathBERT instead. MathBERT is a version of popular BERT language model adapted to mathematical content as our base model. This model is capable of understanding math symbols and expressions to some extent and help us obtain a better representation of open-ended student responses. The other two drawbacks are it's not scalable. So in most of the case, we need to train a separate model for each question. In contexts where reading comprehension or reason is involved multiple questions, maybe link it to each other through the question information provided. In the context of math questions, many questions have similar skills or are different parts of the multi-step questions. Therefore, training a separate automated scoring model for each question will result in models that can only identify typically patterns in student responses to each individual question, but cannot really understand how differentiate good responses from bad ones. The solution for this drawback is applying the in-context meta-learning technique. This technique can reduce the test learning and predict process to a simple sequence prediction problem. Instead of only put the target input to the predicted onto the model, we also concatenate it with the test instructions, some input-output examples. These are so-called in-context input. Then we meta training one model that contain multiple tasks. This task also, in our case, is the questions. During the testing time, we follow the same format of the input and get the prediction. Instruction for our case could be the question test. We will detail it later. So to summarize, we use MathBERT instead of BERT to obtain better math response representations. We also learn a single shared model across all questions, which can leverage shared atom linkage and semantics. And we also add in-context instruction and examples to MathBERT input, which can provide additional input to help the model contextualize to multiple tasks. So here is the overview of our framework. The sequence first transfer into tokens and pass to the MathBERT. And then we can obtain the vector representations. And we use the special token CLS representation and pass it to the classification layer to get the prediction. Now we detail our key technique insight, which is that we need to use a well-crafted input format to provide context to the model and help it to adapt to the scoring test for each question. Therefore, as mentioned before, instead of only inputting the target student response, we want to grade, we also include several other features as the input. For each possible feature, we add additional textual instruction as input to let the model know the semantic meanings. For example, here, for the target student response, the textual instruction is score this answer, and then followed by the test of the target student response. Then the model is know that this piece of the information is for scoring the answer. Here is the template info for question feature. Here is the template for example features. So examples are template responses scores paired within the same question of the target responses. Notice that we can put multiple examples here. The example is a pair, reminder that the example is a pair of the responses with the corresponding score. Here's an overview for all of the features we design as the in-context input. We also have scale and question ID as the optional features. Now let's look at our experimental results. We have two settings for our experiments. So the first one is the generalization to new responses. So we have, for generalization to new responses, we treat this problem setting as supervised learning classification and learn a score model that predicts an estimated score Y by giving X and in-context feature as input. During training process, we make sure to sample enough data for every questions and test how well it's performed on the rest of the responses in the testing dataset. The second setting is the generalization to new questions. So during the training process, we example partially questions with responses as training data set and test how well it performs and how quickly it's adapt to a new unseen questions over here. We utilize 3 evaluation matrices for categorical. The AUC, which is the area under the receiver operating characteristic curve, which is designed for binary classification problem. The higher, the better. And the RMSE, the root mean square root error, the lower, the better. And the kappa, the multi-class Cohen kappa, that is often used for ordering categories. The higher, the better. So here's the result for our first setting. So it's very clearly show that our methods outperform all of the existing methods amongst all 3 matrices. We also conduct the Appalachian study to verify the effectiveness of each component of our scoring method. We say that removing the question task, the contextual instructions, on scoring scale, and also the score example that all result in dropping in scoring accuracy on some matrices, especially removing the score example result in the most significant drop in scoring accuracy. This result validates the effectiveness that providing in context example can significantly benefit language model by helping them adapt to the current question. However, surprising but important results of this experience is that using MathBirds result in a small drop-off in performance on CAPA and RSM compared to using BERT. This observation is counterintuitive since MathBird is especially designed to handle math expressions and train on mathematical content. We then to further examine why MathBird underwhelms on scoring task. We further investigate its performance on subsets of responses divided according to how much math information is contained in them. We divided responses in the test set into two groups. The DMath that contain responses where more than half of the token in the response are mathematical token, while the DText that contains the rest of the responses. So table show here, we see that on responses that are primarily textuals, BERT outperform MathBird, which is suggesting that MathBird loses some ability to encode textual information. And for MathBird, it's outperformed BERT on two evaluation matrices and performed almost the same on CAPA, which indicate that MathBird may have some benefit in handling mathematical tokens, but the advantage may be minimum. Now let's switch to the next setting. We focus on the testing the performance of our approach on generalizing to new questions without seeing score examples and how quickly our approach can adapt to them using few examples. Therefore, we example partially questions with responses as training data set and use the test. During the test, we make n from 0, 1, 3, 5, 7, 10, 25, 50, 80 new square responses per question available to model that already trained on the training data set and evaluated results. We have two settings for our approach. For Meta, we do not further adjust the trained scoring model. Instead, we only feed these new responses and their scores as in-context example to previous trained model. This setting can be seen as zero-shot learning, where we directly test how a scoring method trained on other questions works on new questions without observing any scored responses. For Meta fine-tune, we further fine-tune our train model to the new square responses per question. During this process, we use the other n-1 responses as the in-context examples. The experimental setting can be seen as few-shot learning, where we test how quickly our meta method trained on other questions can adapt to new questions. SBIRT C, which we mentioned before, is the state-of-the-art method on this data set. It's used the similarity to get the most similar responses from history and adopt the grade. By the definition, it's not capable of zero-shot method. And for the SBIRT P, it is another baseline. This method also trains a single and unifying model and can be further fine-tuned, but it doesn't contain examples as their in-context examples input. Okay, so here are the result figures. We see that Meta fine-tune, which is the yellow one, is outperformed the other three approaches on all values of n for all matrices, achieving a satisfactory result when n is small. The performance stabilizes as n increase. and still outperform all other methods. Overall, our meta fine-tune method is significantly effective at warm starting scoring models on new questions since it's able to get a sense of how response should be scored from scored responses to other questions. We also note that in-context example changes the nature of the test from automatic scoring to finding similar responses. As a result, model can learn this task quicker and adapt to new questions using only a few examples. Meta as the zero-shot method, the blue one here, although fails to generate well without seeing any new responses data, still significant outperform the SPERT C from when n is equal to 1 to 3, and performs similar to SPERT P. The advantage only disappears when n is greater than 10. Now let's look at the quantitative error analysis. So first, we analyze the feature. We observe a significant difference between values of the current prediction and values of the incorrect prediction, and we made the following observations. So the scoring method is more accurate at scoring responses with higher percentage of the mass tokens and becomes less accurate when there are higher percentage of the planned test. The scoring method is more accurate when the response contains less images or tables that words cannot represent. The scoring method is more accurate when the average score of the responses is higher. This observation indicate that the model is better at scoring responses with higher quantities. And the scoring method is more accurate at scoring shorter questions, also the shorter responses. We also extract topics and tabs from question tests using BERT-TOPIC. Overall, we see that trained scoring method has better scores that are primarily test-based or involve equations. The trained scoring method has worse scores on estimate type and multiple choices questions. This observation can be explained by language model not being trained to capture numbers since and thus struggle at numerical reasoning. We also analyze the error types the model makes. The first tab indicate that our model can still struggle on mathematical reasoning and handle numerical tokens. It's not very sensitive to operations. The second tab indicate that our model has low tolerance on spelling errors. So this thing is correct, but our prediction is only 2. The third tab indicate that our model may not recognize paraphrase responses. The fourth arrow tab indicate that our scoring method cannot handle response with unparsable formats such as image, table, or attachment. So as a conclusion, we propose a language model fine-tune based method for automatic short answer grading on open-ended math questions. Our method has 2 main components, a base MathBERT model and a meta-learning based in-context fine-tuning method that promotes generalization to new questions with carefully designed input format. Our method outperforms the existing state-of-the-art method on generalization to new response and new questions. So for the future work, we need to develop more effective models for mathematical language since for the current MathBERT, the advantage is still minimum. The complements of the textual information needs to be improved. For example, that we also can consider adding feature like concept tags, information from textbook as actual knowledge, and so on. And there is also a need to theoretically study the fairness aspects of these ASAG methods and ensure all students are treated fairly. Thank you.